Assalamu'alaikum warahmatullahi wabarakatuh. Hello everyone, my name is Hesti Wijayanti. My number students 410141910. I'm from group 11. So today in this occasion, I'm going to present about properly divergent sequence. So you can read the detail of the material in the book on section 3.6. Okay, let's get started to check the material. First is the definition. Let xn be sequence of real numbers. First, we say that xn tends to positive infinity and write the limit of xn equals positive infinity if for every alpha element in real numbers, there exists a natural number k alpha such that if n greater than or equals k alpha, then xn greater than alpha. And the second is, we say that xn tends to negative infinity and write limit of xn equals negative infinity if for every beta in element real numbers, there exists a natural number k beta such that if n greater than or equals k beta, then xn less than beta. We say that xn is properly divergent in case we have either limit of xn equals positive infinity or limit of xn equals negative infinity. We should realize that we are using the symbols positive infinity and negative infinity purely as convenient notation in the above expressions. Results that have been proved in earlier section for conventional limits of xn equals capital L for L element of real numbers may not remain true when limit of xn equal positive or negative infinity. For the example, the first example, limit of n equals positive infinity. In fact, if alpha element in real number is given, let k alpha be any natural number such that k alpha greater than alpha. The second example, limit n square equals positive infinity. If k alpha is a natural number such that k alpha greater than alpha, and if n greater than k alpha, then we have n square greater than or equals n greater than alpha. And the third example, if c greater than 1, then limit c powered n equals positive infinity. Let c equals 1 plus b, where b greater than 0. If alpha element in real number is given, let k alpha be a natural number such that k alpha greater than alpha divided by b. If n greater than or equals k alpha, it follows from Bernoulli's inequality that c powered n equals 1 plus b powered n greater than or equals 1 plus nb greater than 1 plus alpha greater than alpha. Therefore, we get limit c powered n equals positive infinity. Then for theorem 3.6.3, a monotone sequence of real numbers is properly divergent if and only if it is unbounded. Point A, if xn is an unbounded increasing sequence, then limit of xn equals positive infinity. Point B, if xn is an unbounded decreasing sequence, then limit of xn equals negative infinity. For the proving of the theorem, point A, suppose that xn is an increasing sequence. We know that if xn is bounded, then it is convergent. If xn is unbounded, then for any alpha element in real number, there exists an alpha element natural number such that alpha less than x and alpha. But since xn is increasing, we have alpha less than xn for all n greater than n alpha. Since alpha is arbitrary, it follows that limit of xn equals positive infinity. For part B is proved in a similar fashion. So suppose that xn is decreasing sequence. Since xn is unbounded, then for any alpha element of real numbers, there exists an alpha element in natural number such that alpha greater than x and alpha. But since xn is decreasing, we have alpha greater than xn for all n greater than n alpha. Since alpha is arbitrary, it follows that limit of xn equals negative infinity. And then for the theorem 3.6.4, let xn and yn be two sequence of real numbers and suppose that number 1, xn less than yn for all n element in natural number. Point A, if limit xn equals positive infinity, then limit of yn equals positive infinity. Point B, if limit xn equals negative infinity, then limit yn also equals negative infinity. For the proving of the theorem, point A, if limit xn equals positive infinity, and if alpha element in real number is given, then there exists a natural number k alpha, such that if n greater than or equals k alpha, then alpha less than xn. In view of number 1 is xn less than yn, it follows that alpha less than yn for all n greater than or equals k alpha. Since alpha is arbitrary, it follows that limit of yn equals positive infinity. And then the proof of point B is similar. So if limit of xn equals negative infinity, and if alpha element of real number is given, then there exists a natural number k alpha such that if n greater than or equals k alpha, then alpha greater than xn. In view of number 1, it follows that alpha greater than yn for all n greater than or equals k alpha. Since alpha is arbitrary, it follows that limit yn equals negative infinity. Remarks. Point 8, theorem 3.6.4 remains true if condition number 1 is ultimately true. That is, if there exists m element on natural number such that xn less than or equals yn for all n greater than or equals m. For point B, if condition number 1 of theorem 3.6.4 holds and if limit of yn equals positive infinity, it does not follow that limit xn equals positive infinity. Similarly, if 1 holds and if limit xn negative infinity, it does not follow that limit yn negative infinity. In using theorem 3.6.4 to show that a sequence tends positive infinity, respectively negative infinity, we need to show that the terms of the sequence are ultimately greater or respectively less than or equal to the corresponding terms of a sequence that is known to tend to positive infinity, respectively negative infinity. Since it is sometimes difficult to establish an inequality such as number 1, the following limit comparison theorem is often more convenient to use than theorem 3.6.4. And then the next theorem, 3.6.5, let xn and yn be two sequence of positive real numbers and suppose that for some L, capital L, element in real numbers, where L greater than 0, we have number 2, limit of xn divided by yn equals L. Then limit of xn equals positive infinity if and only if limit yn positive infinity. And the proving of the theorem, if number 2 holds, there exists k element on natural numbers such that half L less than xn divided by yn less than 3 divided by 2L for all n greater than or equals k. Hence, we have half L yn less than xn less than 3 divided by 2L yn for all n greater than or equals k. Then the conclusion now follows from a slight modification of theorem 3.6.4. We can show that the conclusion need not hold if either L equals 0 or L equals positive infinity. However, there are some partial results that can be established in these cases, as we will see in the exercises. Okay, I think enough for my presentation. I'm sorry if I have some mistake. There are some mistakes. Thanks for watching. Assalamualaikum warahmatullahi wabarakatuh.